Okay, so we're talking about all pairs shortest path, and this is one of the classic problems in computer science as well as in dynamic programming. So let's dive right into it. Let me share the screen so you can see that. There we go. Okay, so in the all pairs shortest path problem, we are given a weighted graph. So that means this is a graph that has weightage specified on each edge, and that's given by this by a certain weight matrix. And what we're supposed to find is we're supposed to find the distance between every pair of nodes. So not just from one source, rather between every pair of nodes. So for example, the weight of the edge between A and B is 5. The weight of the edge between A and C is 14. The weight of the edge between D and E is 1, etc., etc. But the distance between two vertices is going to be specified by the shortest path. For example, the shortest path from A and B between A and B is the same as the edge. So that's the weight, the distance is 5. But the distance between A and C is given by this shortest path, which is 5, 4, 4, which in this case is 13, which is shorter than the edge. So that's essentially the shortest path problem. It's a very intuitive problem. We can easily be given such a weighted graph, and we can try to find by inspection the shortest path. So let's try to see how we would solve this using computer science, how we would solve this using algorithms, even if we don't use dynamic programming at first. So this is the weight matrix that's given to us, and dij is the distance between nodes I and j, and this is what we're trying to find. So first of all, dij, we can say dii is 0. There's no distance from the node to itself, but what we're trying to find is dij. And one of the first observations that we make is that just because I and j are neighbors, if I and j are neighbors, that doesn't mean we know dij. Just like in this case, between A and C, they're neighbors. wij is known, but dij is not known. So we still have to find it, right? Okay, so what would be our first attempt? If we wanted to write a recursive formulation, we could write it like this, that dij is equal to minimum of over all nodes k of dik plus dkj. Essentially, we are trying to say from between I and j, we'll go to some intermediate node, and then we'll go to the final node j. And we could say that this is one attempt. But the problem with this approach is that we will say that dij depends upon dik, and recursively dik will also depend upon dij. So we are in an infinite loop. Therefore, this attempt doesn't directly work. Now you could say that of course you still have to take a minimum with wij, and that's fine. That's not really the problem, but the problem here is that dik plus dkj is hard to find because dij depends upon it, and that depends upon dij. So that's the basic problem with this first attempt. Let's try to do the attempt number 2. The second attempt here is that we will say from dij, we will go to some node k, where k is some neighbor of I, and then we'll go to that node using wik weighted edge, and then we'll go from k to j. Now this is a little bit cleaner version of attempt 1, but this has a similar problem that dij depends upon dkj, but dkj will similarly depend upon a node x, which is the neighbor of k, and one of the neighbors of x, or one of the possible values of x, that is one of the neighbors of k, is the node I itself. So again, dij depends upon dkj, and dkj depends upon dij. So this is also an infinite loop. So we're not really able to build a clean recurrence relation that we can use, a clean recursive formulation that we can use to build this values dij. So we want to use dynamic programming, and In dynamic programming, if you recall, there are 4 basic steps. Those 4 basic steps are given by the mnemonic NORA. And the first step in that is the notation. Then we prove the optimality, the principle of optimality. Then we develop a recurrence relation. And finally, we write the algorithm. In dynamic programming algorithms, really the notation and the recurrence relation is the key. Once we have a good notation, we can actually solve it. The notation that we have to develop is something that can express the solution as well as any sub-solution. So let's try to see in this case what is a good dynamic programming notation. So I'll present the notation next, but I will mention that while the all pairs shortest path is a very intuitive problem, sometimes this particular notation does not come out as intuitive to many people. So it's an intuitive problem with a counterintuitive solution notation here. So this is what the notation is. It says, now we assume our nodes are numbered 1 through n, not alphabetically, because it only goes so far. If our graph has like 10,000 nodes, it's difficult to come up with the alphabet, but rather we say from 1 through n. So in this case, the notation that we come up with is dkij, where k is written as a superscript here. And this is what it signifies. This is what it stands for. dkij is the length of the shortest path from I to j, but it uses the nodes 1 through k as the intermediate nodes. So in this case, the superscript k represents really a list, and it's a list that starts from the nodes 1 through k of the nodes. Now the nodes were numbered, so the node numbering is arbitrary, but it's fixed. Whatever it was, however they were numbered, as you know, in the graph, the nodes don't have any location element to it. You don't really number them from left to right, top to down, etc. They were just numbered in some order, and it wouldn't really matter in which order they're numbered. But once they're numbered, you keep the numbering as it is, right? Don't change it. The numbering is fixed. So the k, the superscript, represents the list. Now let's make sure we understand. This notation does not say that dkij uses k intermediate nodes. Rather, it just says that you can use any number of nodes, 0 or more, as long as the intermediate nodes are only coming from that set of possible intermediate nodes. So the superscript k represents a list, which represents the universe of the nodes that you're allowed, not forced, allowed to use as your intermediate nodes. So in a way, you can think about it's a distance between I and j in a graph where only the vertices I, j, and 1 through k have been retained, everything else deleted. If it's deleted, that means you can't really use it. You don't really see those nodes, and that's what you can use. So that's what dkij stands for. Like I said, it's counterintuitive, takes some time to settle in sometimes, but that's what it means. Now, another observation we can make is that dkij is a very cosmetic, very artificial notation. In our actual problem, we're supposed to find dij, which in this notation is really dnij, because really we don't have any constraints on which nodes to go through or not to go through when trying to find the shortest path. So that would here be represented by dnij, where you can use any of the nodes 1 through n as your intermediate nodes. And another observation, the final one to make on this slide, is that d0ij simply means that you're not allowed to use any nodes as your intermediate nodes. In that case, it's simply the weighted edge between I and j. Or if you say that there is no edge between I and j, those vertices are not connected directly, then you could say it's infinity, or you could say that it is given as infinity in the weighted matrix. Either of the approaches is fine. So that's what dkij stands for. We are interested in dnij, and d0ij is effectively given to us. Now, what's the beauty of this approach? That we are actually able to build things in a recursive way, which we will discuss next. As you recall, in the dynamic programming notation, algorithm design technique, we have to use we have to prove the principle of optimality. And in this case, the principle of optimality is pretty much represented by saying that the portion of the shortest path must be a shortest path between those subportion nodes as well. Specifically, let's suppose this is the definition of principle of optimality, optimal substructure, that if you have a shortest path from A to B in a graph, then the portion of xi to xj must be the shortest path as well. So in this case, the path A through B is represented as a solution, and the path from xi to xj is represented as a subsolution. So if the solution is optimal, then the subsolution has to be optimal as well. And of course, you can easily prove that using contradiction. If hypothetically you had a shorter path, which is different from this one between xi and xj, then you could replace that into the big path here from A to B and come up with a shorter path which would contradict the optimality of this, the shortest path from A to B. So that's how we know that the optimal substructure holds. Let's look at the recurrence relation here. The recursive formulation in this case, that's the whole reason for doing dkij, is that this allows us a sequence in which to build that matrix dkij. So we observe that the dkij either depends upon the node k or it does not. If it does not, then we can say the dkij is simply the same as dk minus 1ij. So if dkij does not use the node k as in the shortest path, then dkij would just be dk minus 1ij. If it does use the node k, then dkij would be equivalent to dk minus 1 ik. So we would go from nodes I to node k, and finally we would go from node k to node j using the set of vertices 1 through k minus 1 as the possible intermediate nodes. So this is the recursive formulation. Again, let's look at it together. dkij is equal to the minimum of either dk minus 1 ij, in which case we don't use the node k at all, or we do use the node k, in which case it's represented by dk minus 1 ik plus dk minus 1 kj, and you take the minimum over that and you can simply compute it. And we see that to compute dkij, it only takes us a constant amount of time, and this leads us into the direct algorithm. This is a full all-pair shortest path algorithm. It is often surprising to many people that the dk minus, that this all-pair shortest path algorithm is really just a few lines. It is not a very long written algorithm, and you can really write it in about, once you have this pseudocode, you can write it in about 15 minutes or so. It may take you a little longer to generate a test graph and to test it and to validate the answer is right, but the algorithm by itself is very easily written. And let's look at the algorithm again. It says simply we initialize first d0ij to be wij, and again, if wij is not given for certain pairs of nodes, you would represent it as infinity. That's your initialization step. And then you have the recursive step, where you'll go from k equal to 1 to n. So that means first you'll calculate d0ij, then d1ij, then d2ij, and finally you'll compute all the way till dnij. And this is all there is. So for I is equal to 1 to n, for j is equal to 1 to n, and this all happens within the loop of k is equal to 1 to n, we keep computing this. And therefore, we can see that the time complexity of this, there are only 3 nested loops. Within, there is no complication, no increments that are actually varying. It takes a constant amount of time inside the loop. It's only a minimum of 2 numbers. And therefore, the time complexity is going to be order n cube for this part, order n square for this part, and therefore the total time complexity is going to be order n cube. And also we make sure that this algorithm is clean to implement. There is no infinite loops here, because dkij just depends upon dk minus 1 ij and does not depend upon any dk plus 1 values. So there you have it. Now you can also actually clean up the space if you don't want to use order n cubed space, because the algorithm as it's written does take that much space. But if you look carefully, we don't use the dk minus 1 values once dk is available. So you can actually save the space by not keeping the old values. There you have it, all-pair shortest path algorithm. It is one of the classic dynamic programming algorithms. It is a very intuitive problem. It has a slightly counterintuitive solution. The notation is sometimes takes a little bit of time to go through, but that's about it. And there you have your DP algorithm for all-pair shortest path, which fits right into your other algorithm design techniques of divide and conquer, greedy graph, BNB, etc. Okay, there you have it. Keep learning. This material is available on the pages 72 to 74.